Hi everyone, welcome back to ChemHelp ASAP. Today we are going to learn how to assign oxidation numbers. Now we do this to keep track of electrons, usually in a chemical equation. But first we're going to learn just how to assign oxidation numbers both in neutral compounds and also polyatomic ions. Let's get started.
Before we go over the rules, I do want to clarify that oxidation states are not the same thing as calculating a formal charge. So an oxidation state is going to take into account electronegativity of an atom, so it's going to emphasize more the ionic nature of a bond, whereas a formal charge is going to emphasize the covalent nature of a bond and assume that electrons are shared equally. It's nice to be able to do both because they both have their applications. But for this video, we're just going to focus on oxidation states. With that said, let's go over the rules for oxidation states. So rule number 1 here is the oxidation state of an atom and its elemental form is 0. So if you have pure sodium metal, then its oxidation state is 0, as opposed to when sodium is in a compound with a bond. One thing I do want to mention here is there are several gases where their elemental form is actually a diatomic gas. So those gases are hydrogen gas, which is H2. It has an oxidation state of 0. Nitrogen gas, also diatomic, has an oxidation state of 0. Oxygen gas, which is also O2, still oxidation state of 0. Also, most of the halogens are diatomic gases. So you have fluorine gas, chlorine gas, bromine, which is actually a liquid at room temperature, and also iodine, which is a solid at room temperature. For all of these compounds, their elemental form is diatomic. Okay, rule number 2 is the oxidation state of a monoatomic ion is its charge. So going back and using sodium again as an example, when sodium is an ion, it has a +1 charge. That charge is its oxidation state. Next rule, rule number 3, the oxidation state of hydrogen in covalent compounds is going to be +1. That's pretty self-explanatory. Also for number 4, the oxidation state of oxygen in a covalent compounds is going to be -2. The only exception here is peroxides, which you don't run into that often. Your most common peroxide, of course, is hydrogen peroxide. Hydrogen peroxide is H2O2. And so in that case, the oxidation state of oxygen there is going to be -1. For binary compounds, the more electronegative atom is assigned a negative oxidation state, and that is going to be equal to its charge in ionic compounds. So you can think of this as very similar to the oxygen rule, but just for binary compounds. And our last rule here is the sum of all oxidation states for a neutral compound must equal 0. However, the sum of the oxidation states for an ion must equal the overall charge on the ion. Now, we are going to do oxidation states both for neutral compounds and for ions, so you can see how this comes together. So let's start with actually a really simple compound. Here is carbon monoxide. So let's get the oxidation state on carbon and the oxidation state on oxygen. Whenever I am doing oxidation states, I always look to see if there's an element that has a specific rule. And in the case of carbon monoxide, oxygen has a specific rule. It is rule number 4. So my oxidation state of oxygen is going to be -2. Now we need to figure out what the oxidation state is on carbon. So I'm going to call that X. I don't know what it is, but I'm going to use rule number 6 to figure out what that oxidation state is. So carbon monoxide is a neutral compound. That means all of the oxidation states must add up to equal 0. So if you want to put this in mathematical terms, my oxidation state on carbon, which I'm calling X, plus my oxidation state on oxygen, which is -2, must equal 0. Therefore, my value of X here must equal +2. And that is my oxidation state on carbon. Now let's work some more problems. I am keeping my rules for oxidation states in the upper left-hand corner so we can refer back to them as we work through these compounds. I'm going to first work through neutral compounds and then we'll work through ions. So first up, we have nickel oxide. I don't have a rule for nickel, but I do have a rule for oxygen. And of course, oxygen in covalent compounds, the oxidation state is -2. Now, the trick for this compound is I have 2 of these oxygen atoms, so that means this has a multiplier of 2. Now, I do not know what the nickel is, but I can figure it out using rule number 6. This is a neutral compound. All of my oxidation states must add up to give me 0. So I have my nickel plus 2 times my oxygen must equal 0. Therefore, my nickel is +4. Which I will put up here. Easy enough, right? Let's work some more. All right, next up we have sulfur tetrafluoride. I don't specifically have a rule for sulfur or fluorine, but if I look at rule number 5, I have a binary compound. So the more electronegative atom is going to be assigned its oxidation state that it has in ionic compounds. Clearly, fluorine is more electronegative than sulfur because fluorine is the most electronegative atom. So it is going to have an oxidation state of -1. Now, don't forget your multiplier. There are 4 fluorines here. I don't know yet what sulfur is, but using rule number 6, I can find sulfur. So my unknown sulfur plus 4 of my fluorines, make that 1 a little bit bigger, this equals 0. Therefore, my value on sulfur is +4. Next up, I have iron oxide. Now, in this one, we've got a couple different multipliers to work through, but it won't be a problem, I promise. So first, let's do oxygen because I have a rule on oxygen. Its oxidation state is -2. I do have a multiplier here of 4. Iron, I don't know, but I'm going to figure out using rule number 6 because I have a neutral compound. Now I have 2 of these iron atoms. So instead of just calling this X, I'm going to call this 2X. So watch those multipliers. This is a neutral compound, so 2X plus 4 times -2 must equal 0. So X equals +4. So I'll put that up here. So you can see so far we've actually gone through 3 compounds and our first element has ended up with the same oxidation state but very different circumstances. And don't worry, that's completely normal. Now for our last neutral compound, we have P4O6. Again, we have multiple multipliers here. Let's make sure we take those into account. I have my rule for oxygen. Its oxidation state is -2. Its multiplier is 6. And of course, for my phosphorus, it has a multiplier of 4, so I'm going to call that 4X. This is a neutral compound, so 4X plus 6 times -2 must equal 0. So therefore, X is equal to +3. So my oxidation state on my phosphorus is 3+. Okay, so hopefully you're getting comfortable with neutral compounds. Let's work a couple of oxidation states when we've got polyatomic ions. Starting with sulfate here. Initially, I'm going to ignore that charge. I'll show you where I bring that in. I'm going to start just like I start with the neutral compounds. I have a rule for oxygen, and that is its oxidation state is -2. It has a multiplier of 4. My sulfur, I don't know. Thankfully, it doesn't have a multiplier. That makes this a little bit easier. I still am going to use rule 6, but I'm going to use I would say the second part of rule 6. So the sum of all my oxidation numbers for this ion must equal the overall charge on the ion. So my algebra is going to look like X plus 4 times -2. This equals -2. So solving for X, I get X equals +6. That is the oxidation state on sulfur. Let's keep going. Here is another ion, probably a little less familiar, but it doesn't matter. We still are going to use the same rules to find oxidation states. Again, I have a rule for oxygen, so I'm going to use that rule for oxygen. Oxygen has a multiplier, so there's a 2 in front of here. Uranium, of course, I'm just going to call X. So when I set up my algebra, this is going to be X plus 2 times -2. And in this case, I am going to equal to positive 2. Solving for X, I get X equals positive 6. So the oxidation state on uranium is +6. Next up, I have nitrite, a little more familiar territory here. Using my rule for oxygen, it has an oxidation state of -2. I do have a multiplier down here. Nitrogen is all by itself, so it just simply has an X. Setting up my algebra like so. Now this one equals to my charge on nitrite, which is a -1. Therefore, X equals to +3. Again, my oxidation state I'll put right up there. One last polyatomic ion here. Hopefully you're starting to see the pattern. Again, using my rule for oxygen, it has a multiplier. Bismuth does not. So setting up my algebra times -2, this one also equals -1. So the charge on my bismuth is +5, and I will also put that up here. So now that we are comfortable with binary neutral compounds and some polyatomic ions, let's actually put this together and show you a couple of complex examples. I'm still keeping my rules up here in my upper left-hand corner so I can refer back to them. You can see that these examples here definitely have more than 2 elements. So how do we handle this? Well, let me show you how I like to handle it. Starting with potassium permanganate. What I like to do is I like to go ahead and break this up into a cation and an anion. So this becomes my potassium cation and my permanganate anion. This means potassium is already taken care of. I've already assigned the oxidation state. Its oxidation state is +1. But now I need to do the oxidation states on my polyatomic ion. Again, using my rule for oxygen, this is -2. It has a multiplier of 4. My manganese, I'm just going to call X. This is going to be X plus 4 times -2. And of course, this equals -1 because it is a polyatomic ion. Solving for X, I get X equals to +7. So the oxidation state on my manganese is +7. You don't have to break these compounds up into the cation and the anion, but I find that if I can break these into smaller pieces, it's just a little easier for me to assign all oxidation states. Next up is sodium thiosulfate. Again, I'm going to break this up into cation and anion. In this case, my cation is simply my sodium cation. It has a charge of +1. My anion is my thiosulfate anion, which is S2O3. It has a charge of -2. Because I broke it up into cation and anion, I did not have to worry about this multiplier right here. Why do we have this 2 here? Because sodium has a charge of +1, thiosulfate has a charge of -2. To make a neutral compound, you must have 2 sodium cations. But once I pull that cation out and I say, sodium, I know what the charge is on sodium when it's in a cation, then you're good to go and you don't have to do anything more with that. But let's keep going with now our thiosulfate because we have to do our oxidation state on our oxygen and our sulfur. Again, oxygen is going to have an oxidation state of -2. It has a multiplier right here. And sulfur also has a multiplier, so this is now a 2x. So my algebra is 2x plus 3 times -2, and of course this equals the charge on my thiosulfate, which is -2. So solving for X, I get X equals to +2, and that is the oxidation state on my sulfur. I didn't quite leave myself enough space there, so I will just leave this oxidation state down here. Last example, we've got calcium nitrate. Again, I'm going to break this up into cation and anion. So my cation is my calcium cation. It has a charge of +2, which means that is its oxidation state. And now I'm going to do nitrate. Now nitrate has a charge of -1. So what happened to this multiplier? Well, that multiplier only applied to making a neutral compound. So remember, calcium having a charge of +2 means we must have 2 nitrate anions to make a neutral compound. But now that I've just pulled nitrate out as its own anion, I don't have to worry about that too. Now, the one thing I will say about this is easier when you have your polyatomic ions memorized. So I recognize immediately, oh, NO3, that's the nitrate anion. I know what that charge is. That charge is -1. If you do not have the polyatomic ions memorized, this becomes a little bit more difficult, because then you would have to figure out what the charge is on nitrate based on the charge on calcium. Now, you can absolutely do that, but it is easier and faster if you've got those common polyatomic ions memorized. Let's finish up with nitrate. Let's get oxidation states on that nitrogen and the oxygen. Oxygen, as usual, has an oxidation state of -2. It does have a multiplier in this case. And my nitrogen does not have a multiplier, so I'm just going to call it X. So my algebra is X plus 3 times -2. And in this case, it equals -1. So X equals +5. I guess I can just squeeze that in right there. So the math with finding oxidation states obviously is not very difficult. The only thing I caution you about is watching those multipliers.
Being able to assign oxidation numbers is going to help us so much when we talk about redox equations. This is where we're going to need to be able to keep track of electrons and know which atoms are losing electrons and which atoms are gaining electrons. I hope you found this video helpful, and thanks so much for watching.